Hello everybody, my name is Peter Klapper from the School of Biosciences at the University of Kent, and in this video clip I want to talk a little bit about hypothesis testing, critical significance level and p-values. So what do these things actually mean? Now let's assume we have a population here. So this could be, for example, all the students at the University of Kent. And my project was to measure how tall these students are on average. So what I could do is measure all the 18,000 students, or I just simply can take a sample. Here, say I measured, say, 10 students. And my average for the height of these students, we call that X bar. That's the average of a sample. That was maybe 178 centimeters. And of course I can take another sample here. Maybe I took, say, 20 students here, and again I measured the average here from this. So this is my second sample. And let's say this was, say, 185 centimeters. Now, obviously, there is a difference between this average and this average. But the students, they are all students, so they come all from the same population. And therefore, my guess is that, yes, the sample averages are different, but they are not terribly different, because they come all from the same population of students. So this difference here, this difference between the two averages is probably due simply to my samples, due to sampling error. And this is something that is unavoidable when we do statistics. So due to sampling error, we will always have a slight difference between samples, but there's nothing to it because it is simply due to this sampling error. And in fact, these differences are not massively huge, and there is not a huge difference. Now, in this case, I know that these samples come from the same population. Now let's do another experiment where we say, okay, we've got another average in height. So let's call this, for example, XA. And we found that this average is about 202 centimeters. Now, I don't know where this sample comes from. Is it from this population, or is it from, say, a different population like this one? I don't know where this sample comes from. And now my question is this average of 202 centimeters also just a member of this population, or is it of a different population? So this is the big question mark in a way. Or I can phrase that in another way. I can say, for example, I compare X bar A with, say, X bar 2. And I can ask the question, is the difference between A and 2, is it just simply due to sample error? So sampling error. Or is it due to something else? Due to something else. For example, this was actually a sample from say, a basketball team, which has nothing to do with our student population here. So this is the big question. Is this average here similar to this average here, and the difference is only due to sampling error? Or is there something more to it? And I can formulate this actually in what is called a hypothesis. So I can set up a hypothesis, and we usually start with what is called the null hypothesis. Null hypothesis. And it's usually abbreviated H0, like that. And we say, in the null hypothesis, we say there is no difference between the two means, between the two sample means, other than due to sampling error. This is always the statement for the null hypothesis, and you can think of it like, you have null here and no here. So there's no difference between the two samples other than due to sampling error, or I should say perhaps other between the two means of the sample in this case. Means of the samples, to make it even a little bit more punchy. And I can write, in this case, x bar A is the same as x bar, say, 2. So that is my null hypothesis. In one case it is worded, and in the other case it is written as a mathematical expression. I can also come up with an alternative hypothesis. So alternative hypothesis, and we usually call it H1, and this says is basically exactly the opposite. It says there is a difference. There is a difference between the two means, between the two means of the samples. Samples which is caused by not only the sample mean, the sampling error, only sampling error, but also something else. But also another effect. For example, that this is not from the same population, that they are basketball players and the other ones are, normal students. So here we have our two hypotheses, null hypothesis and the alternative hypothesis. And it's always good to formulate these two hypotheses. Now for the alternative hypothesis, I can simply say it is x bar A, the average of A, is not the same as the average for sample 2. We don't say that one of them is bigger, we just simply say that they are not the same here in our alternative hypothesis. Now, if we go back to our example, we said, right, x bar A, this was 202 centimeters, and I think x bar 2, the average of sample 2 was 185 centimeters, something like that, if I can remember this correctly. And now we set up our H0, and we said both samples are the same, or there is no difference between the samples. Of course there will be some difference due to sampling errors, even if they come from the same population. And now we want to be certain to a certain degree. We want to make sure that we make the right decision, that we say yes, they are the same, or no, they are not the same. And this level of certainty that we want to have is called the critical significance level. And this is very often abbreviated as alpha. Now this critical significance level tells us basically how much these samples can differ from each other, and we would still see them as the same. So very often we say we want these difference, or we want to be 95% sure that the samples are the same, are from the same, I should say, from the same population. Or in other words, we want an uncertainty of, let's say, 5%. We want to say that these samples are the same, but we are willing to accept a 5% uncertainty. This is this critical significance level. Or in other words, if these samples are very different, we ask what is the probability that these samples are very different. And it is this critical significance level. And we can write this 5% also as 0.05. This is a very common critical significance level, but we can choose any critical significance level that we want. So what do we need to do? Now we need to calculate, what is the probability, what is the likelihood that these two samples come from the same population. That both samples come from the same population. And then we compare it to our critical significance level. So come from same population. And we can do that with a number of tests. One of the most popular tests is what is called the T-test, where we compare both samples, both sample means, and we get a certain probability. And this is usually called P. So this is a proper probability. Can't write it. Probability. Now it works. And this probability tells us how likely is it that these two samples come from the same population. So how likely is it that the two samples are the same, and the differences are just simply due to the sampling error, or due to sampling error. So for example, if we get a probability of P, in this case, say it is 50% or 0.5, then it means there's a 50% probability that these samples are the same and the differences are only due to the sampling error. Now, is 50% good or bad? Well, we usually would say with a 50% chance that the samples come from the same population, we would probably say, yeah, they are pretty similar to each other. But we have a better criterion. We can compare this, to our significance level, to critical significance level. And I abbreviate that as significance level. We said our critical significance level was 0.05. So we would say if we get a probability, if a probability is larger than our critical significance level, we would say yes, samples are the same, from the same population. Are from same population. Or if we get a probability that is smaller than alpha, we would say no, samples are most likely not from the same population. Samples not from same population. So what we do when we test whether two samples are from the same population, we set a significance level, set critical significance level, and very commonly it is 5%, so 0.05. We calculate the p-value, the probability, and then we compare the p-value with the significance level, with the critical significance level. And if p is larger than this alpha, then we say yes, all is good. Yes, samples are the same, and the only difference is due to sampling error. If p is smaller than alpha, then we say no, there's something else. There's something else, not just the sampling error. There's more to it. And in a way, this makes life quite easy. Because if we go back to our hypothesis, we said this here is resembled by the null hypothesis. Samples are the same. So that is stated in our null hypothesis. And this here would be the alternative hypothesis. So what we can say is if p is larger than alpha, we are happy to accept our null hypothesis. If p is smaller than alpha, then we cannot accept our hypothesis. We have to, our null hypothesis. We have to say that the alternative hypothesis, okay, is valid. And we can phrase that in something that is easy to remember. We can say if p is low, so this means lower than alpha, if p is lower than alpha, if p is low, then h naught must go. Or if p is high, so higher than alpha, and we can write this as p larger than alpha. If p is high, then h naught can stay. I hope this makes sense and it shows you how you can do this hypothesis testing. Thank you very much for watching.